fine now. So excellent.
Okay.
Please take it away.
Okay. Thank you very much, Professor Krishna, for giving me this opportunity to share my thoughts and some research findings. I believe this topic is extremely relevant to the current situation that we are in. And also, I hope this may add some additional factors that may be considered while providing design options for climate resilient geoinfrastructures. I plan to present some general information on climate change in the beginning, and then go on to show the challenges ahead for us in terms of ensuring efficient performance of various infrastructure due to the changing climate. My intention is certainly not to provide any solutions to the problem of climate change, which is, of course, we all understand that's a bigger problem for everyone. And mostly we see the problem as interdisciplinary as well. But I would like to emphasize how soils would respond or possibly respond to the changing climate. I plan to show some previously published experimental results in this line and some new experimental results before providing my concluding remarks. Carbon dioxide level in the atmosphere has increased dramatically in the last 75 years or so. Currently, it stands at about 422 ppm, parts per million, and it is expected to hit a level of 550 ppm or more in 2050. Scientists and researchers explain and justify that the CO2 increase in the atmosphere has led to a rise in the global temperature. When there is evidence and justified and explained well, then we, at least as engineers, should admit that something had changed. The consequence of rise in the temperature is believed to have resulted in longer drought season. Frequency and intensity of rainfall have changed, causing flooding, sea level rise, snowstorm, forest fire, among many other things. This is what we call as climate change, or you can call it a climate emergency. And this will continue unless something is done to stop the rise in CO2 level. The impact of climate change are on ecological, physical, health. Additionally, we witness an altered crop growth, food production, disrupted water supply, changes in the global pattern of nest predation. There are many reports, and many reports are available which provide crucial information on the temperature rise. The IPCC report in 2018, in that report, the suggestion made was to limit the global warming to 2 degrees centigrade and make serious efforts to limit the rise to 1.5 degrees centigrade. So that's the document that we refer to. But if we take a look at the current temperature data and statistics, the average overland temperature has gone up by 1.59 degrees centigrade, and average over ocean temperature is up by 0.88 degrees centigrade. This clearly indicates that what we do or have done in last 7 or 8 years has a little helped the targets. Some reports even mention a shift in the temperature limit to 2.5 degrees centigrade, and efforts should be made to limit the rise to 2 degrees centigrade by 2050. If the rate of increase in CO2 emission continue, which is about 38 billion tons per year, then we could be emitting 75 billion tons of carbon dioxide per year by the end of this century. And the CO2 level, which is currently at 422 ppm, can go up to 800 parts per million. So IPCC has recommended a three-way approach, and many of the energy geotechnics topics are under the first two approaches. A reduction in CO2 may be achieved by using renewables and minimizing the use of non-renewables. CO2 sequestration can be done in ocean, coal seam, rock, oil and gas reservoirs, aquifers. The third aspect, which is extremely relevant, is that if everything fails, then what we are going to do? We need to learn how to live. So that aspect is known as adaptation aspect. And in this aspect, obviously the contribution from engineers, particularly geotechnical and geoenvironmental engineers, industry sectors, sociologists, media, and economists will play a vital role to minimize the climate change impact. There are other efforts which may be made in terms of minimizing the generation of waste, reducing energy use, and more importantly, making lifestyle changes to keep fit in order to reduce the health cost. Published stats would show countries with a low population at this particular condition. The countries, those who have got low population, are generally doing well in minimizing the emission of carbon dioxide, whereas countries with high population struggle to implement the plans. In Wales, for example, out of 50 new projects planned recently, 35 projects were scrapped due to lack of adequate measures with regard to climate change. So the figure on the left shows typical urban development and how the seasonal climatic processes would generally affect the pore water pressure changes and state of pore water during freezing conditions. The factor above and the factor below the ground, they're going to have significant influence in terms of engineering behavior of soils and the components of soil structure and infrastructures. Longer drought season will cause drying of soil, as we all know, to large depths, accompanied by shrinkage of soils, which in turn may cause undesirable settlement. Desiccation cracks tend to generate weak plains for water seepage. Also, at very low water contents, the strength of soil may decrease significantly. Flooding may cause a rise in water table, and soil saturation to large depths may change the heave and magnitude of various soils. During freezing temperatures, soils may exhibit frost heave. Ice lens formation may result in generation of open voids and cause an overall decrease in the strength. Similarly, a rise in temperature following winter will cause ice to melt. The pore water pressure increases due to melting of ice, causing a reduction in strength, and also thaw settlement may occur in many soil types. Most of the infrastructures have been or will experience some of these dramatic changes in the weather patterns. And in many cases, the issue is that soils and structures have never experienced such climates in the past. What you see here are a few adaptation technologies which possibly have direct relevance to climate change and design of resilient geoinfrastructure. I have not included here the emergency preparedness aspects and many other technologies which are being considered and as applicable to a variety of situations that we are facing currently. Sustainable urban drainage system is nothing but construction of underground storage tanks, which can minimize the flooding in urban spaces. The figure you see here is an engineered barrier system. It's nature-based to minimize the flooding in urban spaces, which can either be implemented on top of existing infrastructure or on the top of a new infrastructure. There are significant research works ongoing at this stage in many countries for utilizing many different materials, including the industrial waste. Use of sustainable and nature-based materials are certainly preferred over many conventional materials. So if you are planning to have any of these adaptation technologies and which are nature-based, we must test all these materials to see whether they can cope up with the changing climate. Soil atmospheric interaction is not a new topic at all, but this may be revisited by considering the possible changes in the climate. The first two topics that you see there have been explored in the past, that is cyclic wetting drying and cyclic freezing thawing, whereas the others that you see here are more relevant to climate change scenarios. In each of these processes, that is wetting, drying, freezing, and thawing, the severity may vary as well. For example, partial saturation, partial drying, or full drying, full saturation, or partial frozen conditions, etc. So the severity may vary. So you can have a number of different combinations of these four different seasonal climatic processes. What you see here are some references with regard to the behavior of soils due to wet-dry and freeze-thaw cycling. My apologies for not presenting many other important references in these lines of research due to the availability of space. Cyclic wet-dry tests, which obviously mimic the weathering patterns in summer and in a rainy season. They can be performed in the laboratory by controlling temperature or controlling suction or controlling both temperature and suction. Of course, testing can be done in more expensive triaxial testing environment to replicate or to mimic the wetting drying conditions for different soil types under different stress and hydraulic boundary conditions. What I've shown here is an example of an expansive soil which was subjected to wet-dry cycles involving a change in the drying pattern. A compacted soil sample was prepared and inundated with water, and saturation took place, and it exhibited swelling upon wetting. The sample was dried. Drying caused a shrinkage of the sample. The drying process was terminated at a level corresponding to half the swelling strength that occurred in the first wetting cycle. Then the sample was saturated and dried again, and so on. The soil sample attained an equilibrium after several wet-dry cycles, showing a constant strain of swelling and shrinkage, which is indicated as 3.25%. Then the sample was subjected to more drying, and this time to its original height, and saturated again, and so on. The sample attained a new equilibrium in terms of swelling and shrinkage strengths, and when the equilibrium was attained, the swelling strength is equal to the shrinkage strength. And what you see here is as 4.5% here. In the third phase, the sample was dried to half the swelling strength and saturated again. And the swelling strength exhibited by the sample was same as the shrinkage strength, which is indicated by 2.25%. Further, in fourth and fifth phases, the second and third drying patterns were repeated during the wet-dry cycles. What the results show is that if the drying is more severe than what the soil has already experienced in the past, then both heave and shrinkage settlement magnitudes are destabilized. But if the drying pattern is less severe than what has been subjected to in the past, then equilibrium swelling and shrinkage strengths are attained immediately. This aspect was confirmed with another test. Here is a soil sample which was subjected to cycles of wetting and drying. and the drying was a full drying, and the water content at the end of drying cycle was less than even shrinkage limit. The sample attained an equilibrium with a vertical strain of 14.3%. So the interesting thing to note here is that the swelling magnitude is 14.3% and the shrinkage magnitude is 14.3%. So that is called an equilibrium has reached. Then the drying pattern was changed to a partial drying pattern. The soil exhibited equilibrium swelling and shrinkage strains immediately. The full and partial drying patterns were then repeated in the next two stages. The results again show that if a soil has experienced a severe drying pattern in the past and has attained an equilibrium, and a lesser drying would result in an immediate equilibrium state being reached. What these results show is that it would be prudent to test soils alone or soils along with other components to explore how they would respond to the climate change. Here it is a cyclic freeze-thaw test. Frozen boundary conditions can be imposed by controlling temperature at one end of the sample. Of course, this time it's negative temperature. So we need to take the temperature down below 0 degrees centigrade to freeze sample or to create the frozen condition. This can be achieved by circulating cold air or oil at desired temperatures in a non-contact mode. Also, some researchers have used a metal plate whose temperature has been lowered to any desired temperatures. The important points to note in this kind of tests are the test may be performed in an open system. That means the soil should have access to water during the freezing cycles. The other point is that when we lower the temperature, then at one end of the sample, water turns into ice and frictional resistance get developed. It is not easy to get rid of the frictional resistance, which is also known as ad freezing effect. As you can see in the figure, the researcher has used movable rings in place of a single cylinder in which we have got the soil sample. When freezing front moves downwards, the sample freezes at the top and expands in a downward direction, and the ring gets lifted in an upward direction. So quite a complex testing process when you are trying to do a cyclic freeze-thaw test. I will now show you some cyclic wet freeze-thaw dry test results performed in Cardiff on various materials. The research was performed in line with climate adaptation engineer barrier system requirements. It is very difficult to implement all the seasonal climatic processes in a single test setup. One would require sensors which should perform well in both positive and negative temperatures, talking about positive 30, 40 degrees centigrade and negative probably minus 20 degrees centigrade. So we need to use sensors which will operate in these harsh temperature conditions. What you see in this figure is an apparatus which was designed and fabricated to perform cyclic wet freeze thaw dry tests. There are two PVC molds. One is the outer mold and the other one is the inner mold. So one is sitting inside the other. At the bottom, we have got a water reservoir, which is a cylinder, and it's resting, allowing the porous stones to rest on top of it. And we've got a soil sample with a cooling heating chamber. This is basically a cylinder, closed cylinder, having some vents at the top to which a vortex tube has been connected. The role of vortex tube is to change the temperature at the top of the soil sample. So air pressure can be fed into the vortex tube, and one side you can get cold air, the other side you can get warm air, and you can use cold air to freeze the soil sample, whereas the warm air can be used to dry the soil sample. The water reservoir below, you can see here in the next figure, I will show you that this is the entire test setup. This is the part which I showed you in the earlier slide, and this is a water pot which is connected to the water reservoir such that the water level in the pot can be varied depending upon what kind of hydraulic boundary conditions you want to achieve. It's not a, it looks complex, but it's quite a simple system. Basically, when the soil freezes here, so this inner mold gets lifted off, and you can actually read the deformation of the soil sample under a low stress of 2 kilopascal. Three materials I'm trying to show here. One is space-wide kaolin, which is a clay, Pegwell Bay soil, which is a frost-susceptible soil from England, and here we've got a cement kiln dust, which was brought from a local cement company. You can see the liquid limits here. Space-wide kaolin and cement kiln dust, you can see the grain size distribution here. They can be considered to have a very fine material, whereas the Pegwell Bay soil grain size distribution here, which contains a little bit of sand as well. Here's the textural soil classification chart, and the materials which were tested are shown there. The positions are shown there. Space-wide kaolin is in a clay range, and a silty clay loam here, and then you've got a silty loam is the Pegwell Bay soil. It's okay.
Okay, and done.
Okay, great. Thank you.
Yeah, sure.
There is the compaction conditions of the materials tested. You can see the initial water content, dry unit weight, and the degree of saturation of space-wide kaolin and Pegwell Bay soil were more than 90%, whereas cement kiln dust is about 50%. As you know, cement kiln dust contains a lot of chemicals, and particularly the carbon hydroxide, which are going to get formed when it comes in contact with water. These are the compaction pressure which are shown there. These are the testing conditions. What exactly was the water table position, and what was the temperature at the top and bottom of the sample shown there. During wetting, the water level was at the sample top. It took about 3 to 5 days, and the temperature was ambient. During the freezing condition, the water level was at the bottom of the sample. So the sample had access to water, and the freezing cycle continued for only 1 day, 24 hours. And the top of the sample had the temperature of minus 18 degrees centigrade, and at the bottom, the temperature was about 20 degrees centigrade. Thawing occurred at ambient temperature. It took about 1 to 2 days. Drying, no water was supplied, and it took about 12 to 20 days for different materials. And the temperature at the top of the soil sample or the material was 52 degrees centigrade plus. And at the bottom, it was ambient. Raw data which were collected during the test are temperature at various depths and displacement at the top of the frame. Just typical results on space-wide kaolin temperature during freezing cycles and during drying cycles. At the top of the sample, the temperature was minus 18 degrees centigrade, and water was supplied to the bottom part of the sample. And as you can see, even if you have got a temperature of minus 18 degrees centigrade at the top, the temperature is towards positive when you go deeper into the soil. Similarly, during the drying cycles, but 52 degrees at the top, and at the bottom, you get about 42, 43 degrees centigrade. So these are the results of space-wide kaolin. Wetting caused a little bit of swelling, and then when the sample was frozen, you got a frost heave, then thaw settlement, and then shrinkage, and then wetting again, swelling, a frost heave, thaw settlement, shrinkage strength, and again wetting, freezing, thawing, and drying. What is interesting to see here is that the magnitude of strains that you see there during swelling or frost heave and thaw settlement and shrinkage strain, they're not same, they're different, and because the processes are different and the mechanism governing the volume change due to all these processes are different. The sample showed an uprising trend of movement. So basically, sample is gaining the volume when it is taken through all these cycles. After a few cycles, as you can see, the top level and the bottom level kind of equilibrated. You can say that an equilibrium had reached under these conditions. Note that one cycle is wetting, drying, freezing, and thawing, so all together, and then the second cycle and the third cycle. So you've got a pattern of weathering pattern which is being implemented into the soil, and then the response is shown there. This is the cyclic wet freeze thaw dry test on peg-well bay soil and cement kiln dust. A similar uprising movement pattern was also noted for both. However, the strain magnitudes were different for different materials, and unlike space-wide kaolin, the swelling and shrinkage strains for these materials are very little, but both exhibited significant frost heave and thaw settlement. The conclusions that can be derived from these test results are that materials attain equilibrium state with increasing number of wet, freeze, thaw, and dry cycles. At equilibrium, volume change due to wetting and freezing is equal to volume change due to drying and thawing. Also, plastic deformation can be noted in all the cases. So basically, the materials are gaining the volume. The other important thing to note here is that materials which did not exhibit any swelling and shrinkage strain during wetting and drying cycles can exhibit frost heave and thaw settlement. Now, this is very important since simply using industrial waste and without checking their response to various climatic processes may not be ideal for designing resilient geoinfrastructure. We've got a cyclic wet, dry, and intermittent freeze thaw test. That means the materials were taken through wet, dry cycles, and suddenly you're introducing a freeze thaw kind of weathering pattern. The response was a little bit different from what we observed in the cyclic wet, freeze, thaw, and dry test. With wet, dry strengths, you get swelling and shrinkage strengths, and then you got a frost heave, thaw settlement, and then you got shrinkage to this level, and then swelling and shrinkage, and that is how it continued. As you can see, for peg-well bay soil and cement kiln dust, there is very little swelling and shrinkage, but they affected the frost heave and thaw settlement. As you can see, in case of peg-well bay soil, the frost heave increased with cycles, whereas in case of cement kiln dust, there's a kind of stability. There is not much effect in terms of wetting, drying, which had on the frost heave and thaw settlement. Well, climate change tends to destabilize the equilibrium conditions attained by soils and geomaterials, and hence you can expect the geoinfrastructure to be really stressed due to this changing climate. There is a need for the development of adaptation technologies, and the efficiency of geoinfrastructure and adaptation technologies needs verifying by considering the impact of climate change. The cyclic test, wet, dry test, and wet, freeze, thaw, dry test in various combinations, depending upon the weather pattern at any particular place, may provide some interesting information with regard to how the soils and soil composition are going to respond to the different climatic processes. That is true. And also, you should be able to extract the shear strength and permeability changes that is going to happen due to the volumetric changes. This part of the research work was funded by EPSRC, and thank you very much.
Thank you so much, Professor Tripathy, for very nice presentation. I think what you made everyone aware of is to look at these wetting, freezing, thawing, drying cycles that are happening with the climate change that needs to be taken seriously. And I know we used to do it before,